Hello, welcome everybody to Matea Valley's calculus tutorials. We will begin with the most basic concept of calculus, the rate of change, or derivative. In complex functions, it is rather difficult to find the slope at a point using conventional methods of rise over run. For example, when you pick a point far out, such as the point A, where the point is f of A. You find that the slope is not a completely accurate representation, the slope being change in y over change in x, which is f of x minus f of a, all over x minus a. But it is known that when you approach the point x here, that the slope becomes a much more accurate representation of the actual slope at f of x. Therefore, a limit is created where a point extremely close to the other point, where the distance is considered h, and the point is considered f of x plus h. The slope at this point would be, once again, change in y over change in x equals f of x plus h minus f of x, all over x plus h, which is this point right here, minus x right here. This can be simplified to become f of x plus h minus f of x, all over, since the x's go to 0, h. So a limit is created where the limit as h approaches 0 of f of x plus h minus f of x all over h becomes a derivative. This is known as the limit definition of a function. To see an application of this, you would simply define f of x as a function, in this case a very common function, x squared. F of x plus h would simply be x plus h squared. So the limit as h goes to infinity of f of x plus h minus f of x all over h is actually the limit of, as h goes to 0, of x plus h squared minus x squared all over h. You would expand this right here to become the limit as h approaches 0 of x squared plus 2xh plus h squared, all minus x squared over h. The x's here go to 0, so you find that the limit as h goes to 0 is actually 2xh plus h squared, all over h. However, you can factor out an h from here. So the limit as h goes to 0 is h 2x plus h, all over h, where the h's cancel, divide to 1. And then you can simply plug in 0 for h, so h goes to 0, and you find that the limit is actually 2x. This is a derivative of the function x squared.